10.3, Example 8. In this example, we're going to look at how to find the area between two different polar curves. The area between r sub 1 of theta and r sub 2 of theta, where those two functions are polar functions in terms of theta, between alpha and beta it's going to be the area of the outer function. So r sub 2 is the outer function, and r sub 1 is our inner function. So polar doesn't follow the traditional up minus down or right minus left. It follows outer minus inner. So you have to use the outer one minus the inner one. And then you can simplify that down to one integral. In example 8, we're going to look at the area of the region that lies inside of the circle r equals 1 and outside the cardioid r equals 1 minus cosine theta. So in order to know which one is my r1 and my r2 and to find my theta values, I'm going to want to graph them both. Alright, so what I did is I first just imported my graph that has them all just highlighted and colored however it came. And then on the right, I also put them without any shading. Because on the right, I'm going to show you exactly which part of this graph you're going to want. So we want it to be the inside of the circle, so the inside of the circle, and the outside of the cardioid. So the outside of the cardioid is this part here. So that's the part that we're going to want. So I'm just going to highlight that a little cleaner. So the yellow highlighted region represents the area that we want. So the next step is to find the intersection points. So I need to find my theta values here and my theta value here. And in order to do that, we do that the same way we did that with our other integration functions. It was we set them equal to each other and solve. So I have r sub 1 was equal to 1 because it was a circle with radius 1, and r sub 2 is 1 minus cosine of theta. And so now all I need to do is set them equal to each other and solve. So I get 0 is equal to cosine. So theta is going to be pi over 2 and 3 pi over 2. Now when I integrate, to make it a little easier, remember I can also make this equal to negative pi over 2. Right? Because if I have a circle here, this point is pi over 2. This is 3 pi over 2, and also negative pi over 2. Because what I'm really looking for is this chunk here. So if I go pi over 2 to 3 pi over 2, it's the wrong piece. Because that's not what we want. We want to start here and go like this. So we want to start at negative pi over 2 and go to pi over 2. So the next step is to go ahead and set up the integral. So I'm going to set up my integral, and it's going to be from negative pi over 2 to pi over 2. And then when I set up my integral, I'm going to think my outer one minus the inner one. And then d theta. So now what we need to do is determine our outer function and our inner function. So to do this, I'm going to go up to the graph, and I'm going to show you how to do that. What you do is you pick a random theta value. So I'm going to pick my theta value. So what you want to do is pick a random theta value in which our region lies. So we only want to go to this dot. So we want to make sure we're less than pi over 2. So I'm going to pick theta, I don't know, we'll say here. This is my theta value. And again, it can be any theta value between your two limits. It could also be here. That's a perfectly fine theta value. And so we want to look at the outer and inner. So here's where this intersects, here's where it intersects, here and here. So we can see that the green graph is outside of the blue graph here. So then the circle is our outer function, and the cardioid is our inner on this interval. If we were to look at the area over here, for example, it would be different because the cardioid would be outside. So for our problem, the circle's outside, the cardioid's on the inside. So we set up our integral from negative pi over 2 to pi over 2, and then it's going to be 1 squared, because that's the circle, minus 1 minus cosine of theta squared d theta, and don't forget to put the 1/2. All right, so we can work this out now. We get 1/2 integral negative pi over 2 to pi over 2, 1 minus, and then I want to go ahead and square that. So it's 1 minus 2 cosine theta plus cosine squared theta d theta. And then, using symmetry, I'm going to go ahead and look at our graph one more time. We can see that if we were to divide the graph in half right here, if I were to cut that graph in half, then the area up here, then the area from 0 to pi over 2 would match the area from negative pi over 2 to 0. So because of that, I can go ahead and rewrite my integral as 1/2 times 2, the integral of 0 to pi over 2, and then it becomes 1 minus 1 plus 2 cosine minus cosine squared. So the 1's cancel, gone. These are going to cancel, gone. So I have the integral from 0 to pi over 2, 2 cosine theta minus cosine squared theta d theta. So the next step is to go ahead and simplify this. We need to get rid of our cosine squared in order to integrate. So then it becomes the integral from 0 pi over 2 to cosine theta using our double angle formula, negative 1/2 cosine 2 theta plus 1. And then we're just going to go ahead and simplify that a little bit. 0 pi over 2 to cosine minus 1/2 cosine 2 theta minus 1/2. And now we're all set to go ahead and integrate. So when I integrate 2 cosine, I'm going to get 2 sine. Here I'm going to get minus 1/2 sine 2 theta, all divided by 2, minus 1/2 times theta from 0 to pi over 2. So when I plug in pi over 2, I get 2 times 1 minus 1/4 times sine of 2 times pi over 2 would be sine of pi, so it's 0, minus 1/2 times pi over 2, and then you go ahead and plug in 0. So this would be 2 times 0, 1/4 times 0, minus 0. So all of this just goes to 0. That's going to 0 out. And so I get 2 minus pi over 4. And that's it.